Hello, this is the fourth video to Introduction to Differentiation. You might be already tired of this, but let's work one last example on how to find the derivative of a function using our definition. Let's rewrite our definition. It's never bad to just make sure that we still remember it. So the limit as delta x approaches 0 is f of x plus delta x minus f of x over delta x. And so we know that f of x plus delta x in this case is just square root of x plus delta x minus the square root of x over delta x, and that is as the limit as delta x approaches 0. So let's erase this. Okay, so this doesn't seem so easy anymore, right? You cannot just go ahead and erase this too, because obviously that's what my professor used to call voodoo math. So you don't want to do that. That wouldn't give you the same function. This function and this function are not the same. These two are not equal. Okay, so how do we go about finding what this function can be equal to? So as you might have learned, in order to get rid of square roots, what you can do is get kind of a difference of squares. So as you might recall, if you multiply x minus a, oh no, let's just put a minus b times a plus b, and you were to multiply this, you get what is called difference of squares. So you get a squared minus b squared. So we want to do exactly that. As you can see here, if a is just square root of something and b is the square root of something else, and squaring it gets rid of the square root, of course. So we want to multiply this by x plus delta x plus the square root of x. And we want to do that also to the denominator, because if we didn't do it to both the numerator and the denominator, we would be changing the function itself, and we don't want that to happen. So we already know that this is the difference of squares, so we can just say that it's x plus delta x squared minus the square root of x squared over delta x times delta square root of x plus delta x plus the square root of x. So now we can get rid of this bottom portion. And so now we just squaring this is trivial. You can just get rid of the squares and get rid of the square root, like so. And so now you see that the x's cancel, and you're left with delta x over delta x, the square root of x plus delta x plus the square root of x. However, delta x and delta x cancel out, and you're left with 1 over the square root of x plus delta x plus the square root of x. But now we want to find the limit, that we always do, as delta x approaches 0. And so this just approaches 0. So we're left with 1 over 2 square root of x, because here we're left with square root of x plus square root of x, and that is just 2 square root of x. And so this is our derivative of the square root of x. So if we have to find the derivative with respect to x of delta of the square root of x, we get that it's 1 over 2 square root of x. But this introduces a very important concept, which is that the domain of f of x and f prime of x are not always the same. So you might ask yourself, maybe you don't remember what domain is, or how can this simple result that we get here, how can this prove that the domain of f of x and f prime of x are not always the same? Well, you see that here x could be anything. X could be negative infinity or whatever. We just get imaginary values, but there's nothing too different about it. And if we have any restrictions with square root of x, maybe we don't want imaginary numbers or whatever, well, we have exactly the same restriction right here. We have a square root of x as well. So any limitations, any numbers that are not in the domain of square root of x, they would also not be in the domain of 1 over 2 times the square root of x. However, there is one limitation that our derivative right here has that our original function didn't. And that's that, as you might recall, the denominator should never equal to 0. That if it's equal to 0, then we get undefined. So that means that maybe we have an asymptote, a hole, or just something weird there, and the function is not defined at that given point. And so actually here we have our denominator, and it is 0 when x is equal to 0. So for our derivative, x cannot be equal to 0, and so our domain does not contain 0, while our function does, our original function. So that is just a concept that I wanted to introduce, so that you understand that you cannot always exactly know what is going on the derivative just by briefly looking at the function. And also something to keep in mind is that as you move on and learn the shortcuts, you will see that when you have a constant slope, the derivative is equal everywhere. For every x. But when the slope is not constant, the derivative is different at every point. For example, here, if you were to graph the square root of x, you would get something like this, right? And so here you see that our slope right here, which is, our derivative, which is the slope of the tangent line right here at this point, and the slope of the tangent line, let's change color, at this point are not equal. It's very easy to see that. This one is horizontal, more horizontal. This is a little bit more vertical. So it's very easy to see that the slopes are not equal. However, if we have another function, which is just a line, it has constant slope, so constant slope means that the slope never changes. Our tangent line right here has exactly the same slope as the tangent line right here. It's the line itself, because there's the slope at any point is just the same everywhere. And so that is something to keep in mind. And so the derivative of a linear function, so the derivative of a linear function is just the slope. So I invite you to find f prime of x of a half square plus 2. Find it using our definition. Limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And I guarantee you, I promise, that, sorry, I wrote this extremely badly. So that's f of x, that's not f prime of x. And so if you try to find the derivative of that function right there, I promise that you will get a half. So try it and you will see.